All right, is that decent? I mean, the biggest problem I've noticed is just setting it up, right? There's not enough emphasis on modeling a problem with variables. So now you just plug this in there and you just do like we just did. We find, in this case, we'll find FW and FH, or SW and SH, right? SW equal to 0, SH equal to 0. Okay. Is that decent? I guess I don't want to finish that out, because if we got to the hardest part, people can normally attack the derivatives pretty well, especially here.
You would do the derivative of that, right?
Well, once I plug that in, so I
Once
get
you plug,
S
okay,
equals, what would it be, 32,000 over H. Is that cool? Because I get a W that cancels.
Plus 2WH plus 32,000.
Yeah, 2WH plus, what will it be, 64,000 over W. That's after plugging that in for L. Now you can figure out SW, set it equal to 0. Is that cool? I mean, once you get the function set up, you should be able to attack it. And now you see sort of how to make sure you put the points together correctly. They actually go with each other. You get something from something else, those go together to make points. There's not a bunch of numbers you just got to figure out, hope and pray, throw them together. Okay. Anything that talks about closest or minimize the distance, remember, don't forget you don't have to use the full square root over that distance formula, remember? You don't have to do d, you can do d squared. That's the main reason why I wanted to do this problem on this handout, is to remind you guys, if you minimize d squared, the distance squared, you've automatically minimized the distance itself. So please, dear God, don't take derivatives with this big-ass square root over everything. It'll work. But I don't know. Okay. If you weren't here last time, I made section 14.8 extra credit. All right, somebody who's online remind me I want to make that worth 0 points. You still do it, and at the end I'll just add stuff on depending on how many you got right. But I don't want it to directly affect your grade in there. Okay. So what we're about to do is we're about to get into integrating underneath these surfaces for some region in the input plane. Oh God, let me say this again. So we start off kind of nice. There's a million different ways I can do this. I'm trying to figure out the best order in which to do things. Because there's some skills we have to know. Yes?
For like a square region or a rectangular region, isn't it pretty simple? Just integrate with respect to x and then y?
Mm-hmm. I do want to get into a little bit about why that's allowed.
Okay.
And also, I kind of like to discuss the more general idea and then come back and say if it's just a rectangular region, then it really is simple. Because the region that we're talking about, so what I want you to realize, for example, back in Math 180, we could do the integral, we can find the area under some function for any given segment on the x-axis, right? So now what's different is we're talking now about finding the volume under a surface for any region in the xy plane. You guys, because this used to be our inputs, and this was our output. Now I got inputs that live in 2 dimensions. So I can have regions to find. I can have a rectangle and say, what's the volume underneath this surface above the rectangle? Or I can have a circle. I can even have a line. We're going to do line integrals eventually. I can have whatever. Some funky-ass shape in there. So one thing we have to be good with, and one thing on this handout that we're going to do today, is how to change it from dx dy to dy dx. What if I want to do the x's first? So we have to have that skill. The really nice thing is it's better drawn than I could ever draw it in the book. It's a beautiful analogy with Riemann sums. What?
Riemann sums.
Yes.
Oh God.
So Riemann sums. Who can remind me what the hell that was? So if I wanted to draw some representative parts that I need for Riemann sums.
Rectangle.
Rectangles. I like it. And there's a billion different ways, more than you've ever discussed. about how to define those rectangles, right? You got left end point, right end point, midpoint. You can have an arbitrary point in the middle. You can have the whatever you want, to be honest. And then you got trapezoidal rule. You guys learned that last semester or whenever you took math 2A, right? Then you learn trapezoidal rule, Simpson's rule. All right, engineers use that a lot. So if I used, for example, left end point, blah blah blah. Cool. This is now in 3 dimensions. Let me try to show you what it would look like. Oops. You were where you wanted to be, Jeff. That's pretty good. Go back. So here's the old one. Here's Riemann sums. Back in Math 180. Now what we're doing is here. We have some region, and in section 15.1 they start with that region being rectangular. What I really want to do is discuss, it could be any shape, and then if it's rectangular, it's easy. So I'm trying to find the volume between the surface, and when I say volume, hopefully you remember what kind of values could you have coming out of integrals that don't make sense with area or volume. You can have negative outputs, right? But we just understand that to be the negative of the area. It just sort of tells me direction. Yeah?
With any shape, but you have to integrate with respect to a function.
Yes. Your limits will have functions in them. Don't freak out. Well, you can freak out for right now. Hopefully I'll take the freak down factor down a little bit. Now here's that same thing. They zoomed in a little bit. So just like we could break the x-axis up into little segments, I can break the region down into little squares. And now instead of talking about adding areas of rectangles, I'm now talking about adding volumes of these little rectangular solids that I get. All right, so it's very similar to letting n be 8. So then you would break up your region into 8 squares, and then you'd see get the volume of each one of those and add them up. That's basically what it would be. Now what's different is I have to go in 2 directions. I have to move along the x-axis and I have to move along the y-axis. So you don't get a single summation. You get, where do they have this bad little boy? Here it is. Get this guy here. Oh yeah.
Summation of summations.
Yeah. Right? This looks awesome. So you just take my word for it. So we got volume is, what do they use? I and J. N. I got a little asterisk.
There are stars now.
So what do you think this is? Remember back in Math 180, it looked like this here. And this was the, true, but tell me more geometrically. More geometrically. It was the base of the rectangle. I love it. It's the width of the rectangle, and then this was the height. Same thing here, right? That's still going to be the height. Notice that here I could pick a point anywhere in the little interval of delta x. I could use the left end point, the right end point, the midpoint, but really I could use any damn point I want to because I'm letting it get infinitesimally small. So no matter what you choose on the way to having no choice, right? Here I've got to pick a point in that little square that I've broken the bottom up into. So my point, my little xi, yi is going to be some point in that little region, that little square right there. Yes, sir.
So it's basically the area times a fraction of it? Is that what we're doing? Or am I thinking something?
I'm not sure.
Okay, never mind.
I want to look at a specific example of a double summation just to show you that it's not that horrible. What if I had this? Let's do 0. Why not? Double sum 1. So who remembers what the sum
42.
from j equals 0 to 6 of 1, what would that be?
6.
6, I love it. If you sum 1 up, so 1 when j is 0, 1 when j is 1. Actually, it would have to be 7, so let me not throw us off. I don't want to do that. So from 1 to 6, it would be 1, 2, 3, 4, 5, 6. So that would be, so so watch what's happening then. I'm doing the sum of these sums. So then sum equals 1 to 7 of this guy was 6. 6 times 7, 11. So you can think about this as saying, okay, what if I have this block that is 6 by 7? Right? So instead of saying I've got 6 7s, let me make sure you guys are. What are we talking about right now? Somehow we're talking about the definition of multiplication, right? But go with me. It's kind of neat. So instead of just saying I've got 6 7s, so I'm going to add up each of these. That's what this does. I can go one step back and say I have 6 1s, but for each one of those, I got 7 of those. So I'm going along the x direction and along the y direction. That's what's really happening. All right. So I want to show you this picture. Well, shoot, I should have used that picture I had right there. Let me show you this. Okay. Trying to figure out what order to do this stuff in. If I wanted to, so here's my surface. You guys see that gray? That's the surface. That's the surface right there. Is that cool? Yep. That little undulating dude, right? Looks like it's got a saddle point, all kind of stuff. Yeah. And I'm gonna integrate over this square right here. Maybe it's not square, but the green and the red are sides of it. So if I here we go. So now watch this. That integral right there would be a nice, that's almost too nice, but let me push it back a little bit. Let's see if you guys can see that. See this here?
Yes.
So that area is a Math 180 question, right? Every time I move along the y-axis, so this is letting my y stay constant, so I'm letting my y value change, that I'm keeping constant, and then I'm moving along the x-axis. So for every y value I pick, I could calculate an area associated with that. So for this y value that I got picked, there's this green area that goes with that. So how would I end up getting the entire volume of this under this surface then? What would I want to do with all the possible areas? Just add them all up. And how do you add them all up in calculus? Because this is a continuous thing.
Integral.
With the limit of the summation, which becomes the
Integral.
So you can imagine the same way that this guy becomes this. This guy, the limit, as n and m go to infinity, becomes a double integral. And I really want this to make sense. So we know that the summation symbol by itself, back from Math 180, when I let it go to infinity, the number of rectangles is adding up over. That becomes the integral symbol. And the integral symbol is just a long freaking S. If you didn't know that, it really is. And it just stands for an infinite sum of little infinitesimals. All right, maybe. So what I'm trying to do now is to get a volume, I want to add up all the areas. Right, so in this case, what variable am I allowing to change to vary up here? The way I'm doing this, what variable am I allowing to change? Yeah, good. I like because area is going to be dependent on
X.
Exactly. So to find this area, I've got to let x vary. Right. So that for that area right there, y is a set value. I can integrate, I can get a nice Math 180 integral to find that area. I just have to know what that surface is, what that line piece of the surface is. I can find the area underneath it, just like we did back in Math 180. So what I want to do here now, this guy, how do I find each area? It's going to be its own integral. So really what I'm doing is, I'm adding up a bunch of areas. So I'm integrating a bunch of areas, but how do I get each area that I want to put into my integral? I integrate the function so that looks a lot like this. An integral f of xy dx dy. What do you think dx dy? Dx dy would be a little tiny infinitesimal area. dA. Right. Okay, maybe. So I really want you guys to keep that in mind. That and would the order matter here? The way I do this, I did this just because I happened to click the X bar, the X box. I did this where I let X change for my each area, and Y kind of found each area. Are you guys cool with what I just said? So right now I've got a Y value, so I found this area, and how do I find that? How do I actually calculate the area? I let X vary, right? Okay, good. Maybe. Would it really matter if I did this the other way around?
No,
Why not?
because they calculate the same thing. They calculate that surface.
True, and the big reason right now is because the region I'm calculating over is just a rectangle.
Yeah, but couldn't one way be easier to evaluate?
There you go. One way could be impossible, and the other way could be possible. It depends on what this function is, right? Obviously, if this function is e to the x squared, I probably don't want to do dx first because it's impossible, or I got to bring infinite sums, which I really don't want to. But maybe if I do the dy first, it brings in something that wasn't there before, and then it makes it possible to do. Okay. So that is the idea behind double integration. And the really funny thing is I can recapture stuff that I've done in 2 dimensions with this. I don't know if I really want to do that, right? Maybe we can do that later once we do some of these just by themselves. Give an example. Let's start off nice. Let's do this here.
So are you finding the whole area of the entire green box, or are you finding just the surface area?
So I'm finding an area of this green, right? This green is just 2-dimensional. Is that cool? I can look at it straight on. Right? So if I find all of those, if I find an expression that represents all of the areas under the curve, I can then add up that, integrate that expression in the y direction, right? Okay, I like it. So let's try a problem. Let me take one out of the book here. Sure. Well, okay, I like it.
So to find this one, you would have to integrate it like 3 times just to find the entire thing.
Say it one more time.
You'd have to integrate it like 3 times, right? Because you have different levels of the Z.
No. Do you see how this picks all of it up?
Right. If you're trying to find the entire thing, you have to go from one point to the center point where it's like maximum.
No. This is following it. This is following it. Yeah, so now you can think of it like a scan, like a CAT scan, right? So it's capturing all that because that integral is going to be defined off of that function. So it's going to capture all those waves in the function. Okay, so if I set y equal to a single value, so here, if I let y be, what you got there? Pi over 3. So no, too bad for you, John. Pi over 6 too bad. If y was pi over 6, if I just set it to be pi over 6, I could find the green, the area for that y value, right? So let's try to set this up. Let's see if you guys can see if there's a better way to do this or not. So my first question is, see how they just have a dA here? Do I want to make it dx dy, or do I want to make it dy dx? And the reason that one might change is, like I said, if there was an e to the x squared, I'm not going to do dx first. I'm going to hope to God that if I do dy first, it'll help me figure that out. So let's try to set it up both ways. Let's see if there's a difference. So if I do dy dx, and you can do this for yourself if you want to, just so you get used to where the limit should go. What limit should go on this integral right here? 0 to pi over 4. I love it. So the inner goes with the inner. Right, and this is the outer integral. So number one is you've got several limits. Where the hell are they going to go? Well, that dy goes with this integral symbol. So that's going to be the one that tells me what the hell y does. And realize this too. This is exactly like partial integration. That's actually the name of what we're doing in the interior. When I do this dy, I'm assuming x is a constant, because it really is. I don't know if you guys see what I'm saying. It really is a constant, because when I find this expression for the green area, I'm assuming I'm at some constant value of the other variable. So it is exactly like partial differentiation in that respect. Yeah.
It's just the difference between saying that this can be whatever it wants. It can only be one of it at one time. Whereas the other one, it can be everything at one time. Almost.
Sure, I got you. Yes, I think. Yes. Yeah. This at any specific instant, any specific value of x, I'm going to find the area for that. So x is a constant relative to y. Y can change as x stays the same. So that's what the inside means. And is that an easy integral to do? Do you know what the integral of secant squared is? Yeah, okay, good. So that's the kind of thing you think about. If I did put dy first, can I do the integral in there? If not, you're going to want to change it around and hope to God it works out. What's going to go on the outside, of course? 0, 2. So that x can come out of there even if you want to. Remember, you can't take variables out that deal with what you're taking the integral of. Well, x is not y, so it could come out of there if I wanted to, just to make sure I don't freak myself out and make x squared over 2 there or something.
Never mind. I was trying to say that.
All right. Okay. One thing you want to really, really pay attention to, that if I do write it like this, which is not a bad idea necessarily, the integral dx still has this whole thing in it. So you can't just make that x squared over 2 right now, because I don't even know what function I'm integrating yet, because I don't have this entire thing yet. Now on this, with rectangular regions, what's really nice, and what won't be so nice, what Micah picked up on, is that the limits are not going to be constants for non-rectangular regions. They're going to be some function. I'm going to go from a squared to a square root or something. That sounds a lot like, and we're not, compared to this, it should be rather easier to do this. Remember the rotations of things. Remember that? Oh, yeah. Have this little, in fact, this is this thing, and you rotate it around this way, and the radius is here. You remember those? Washers and discs and stuff? Oh, I was hesitant to bring that up. Related to that, this should be easier to attack, because it's just 2 integrals in a row. Now, if you suck at derivatives, and therefore you suck at integrals, this is just going to double suck, right? I mean, I can't help you there. But if you're good at that, you should be like, oh, thank God, this is not too bad. So what do you get for the inside integral then? Yeah, tangent y from
Pi to 4.
0 to pi over 4. Yeah, I'll have to remember you in a minute. I want to do that still. dx. So then I get tangent pi over 4 is
1.
beautiful 1. Tangent of 0 is
0.
0. Yes, but why?
Because x squared over 2.
Good.
Pi over 2.
X squared over 2. From 0 to 2. You understand why I have to ask you, okay? Because people, once you start adding steps in, we tend to forget that we have to integrate before we throw, because our brain goes, we've done enough already. We must be at the point where we can plug something in. All right, maybe.
So
This feels like partial differentiation in a way.
when you get those values, what do you do with those values?
Which values?
The values that you find for x, y.
These here? Or no? What do you mean?
Yeah, so when you, after you integrate, you find the x and you find y, you just put them all in a vector or a point?
No. You're done. So what we just did is, this is a surface, right? If I graph this in Wolfram Alpha or somewhere, I'm going to get this surface. And what we just did is we figured out the volume under that surface over this rectangular region. So in the xy plane, I got this rectangular region. And the surface comes and it does its stuff, but I just figured out the volume under the surface over this region. That's what we just did. And it comes out to be 2. Now, that's really nice. It's almost too nice to believe it could be the right answer, but it is. All right, maybe.
So is that, what is that? What is 2?
2 is the volume under this surface over that region.
But you know how if you took like the integral of, say, like a velocity,
Oh,
and you got,
I don't know what this surface represents. So you're right. If this surface represents some physical, like a flow of a field through some area, then the integral would be the total flow over some time or something. It depends on what this actually represents. It didn't give me something for this, so I don't know what this represents. But you don't need all that. It could still be considered as some physical room with a weird ass ceiling that has this shape to it. And you're like, well, how much volume is there in this little storage shed? If the floor of the shed is this rectangle, and the surface in the ceiling looks like this, how much volume is there to put stuff into there? This weird old man, he made this thing according to this function, his favorite function. Right? Let me see if I can graph that real quick, because now I'm curious. Can't do anything real quick on these. Let's see. Oh, you're jinxing yourself now, Jim.
that's a ceiling? That actually looks kind of cool.
Yeah, it does. Don't let the people talking about the new convention center look at this. Probably try to make. All right, so let's see if we can identify what region we're talking about. So what was it? Y went from 0. So I got my Y going the wrong way. Where's my X? There's my X. Good Lord. Okay. Oh my God. This is some freaky stuff. So here's X and Y. So X goes from 0. Here's Y. Sorry. Where's my X? Is that one? So X went from 0 to whatever it was. 2. Can't quite see 2, but so yeah, this would be my roof. It's not the best function. We'll talk about it in the terms of a roof, but oh well.
Holes.
Too bad. And of course, they chose this. Where would this function have a problem?
Blah. Pi over 2.
Pi over 2. I like it because it would be over cosine. I was like, blah is not the right answer. Yeah, so this is over cosine. Cosine is a problem with pi over 2. And then have a problem, but it would if it was under 1. So we didn't go up that far, did we? So if I look at my y, I only go from 0 to pi over 4, and pi over 4 is less than 1. So I really just pick up a little bit of this. So it's like a ceiling that maybe looks like this. And that's completely possible. It's not impossible, right?
They used to
The one that the ceiling goes to infinity, that might be impossible, right? But thankfully, we didn't go that far. You guys, am I with me here? I mean,
So if we
yes.
went to pi over 2, that's when it would have went to.
Yeah, then you're back in 180 where your integral can't go over somewhere that the function is discontinuous. Then it's an improper integral at the very least, if not impossible. Yeah. Yes.
It's going to be lovely to try to get the negative areas as actual areas.
Oh, there might, depending on the problem, most problems should allow for that because that would mean like, example, if I was talking about flow through an area. So again, if you've taken any physics, you know that you can talk about water flow, you can talk about electric field flowing through, you can talk about magnetic field and all that kind of stuff, right? The flux, I like it. Through, yeah, you know, we're not. If I was talking about the flow through an area, come back at me because I just forgot what you said.
I was just going to say, if you're trying to find an area that would end up as negative and canceling something out.
Oh, okay.
then
The negative and positive could just denote direction of flow.
Yeah.
So I can talk positive would be flowing into something and negative would be flowing out. So over a period of time, I could have a net flow of 0. So I don't want to make all my negative parts positive.
But if you wanted to find total flow.
Exactly. So that would be like finding true distance travel, not just displacement. Do you remember that whole thing where you had to draw the little thing and see where the